Hi everyone, I'm Masood Agassi, and in this video series we are going to learn about processes and threads. Whether you are new to this topic or want to understand it better, this series will explain everything in a simple and practical way. Let's get started. In the last part, we learned about operating system responsibilities such as CPU and memory virtualization, the definition of processes and threads, process creation and management, memory allocation and virtualization, and finally various states of a process. In the last part, we learned that the operating system should have some policies to run multiple processes concurrently through time sharing or parallelism. But how should the operating system decide when to stop the execution of a process or decide which process should be executed next? Consider this example in which we have 3 processes to be executed and only one CPU core. One way to share the CPU time between these processes is to let the processes themselves decide when to stop execution and allow the operating system to start executing another process. This approach is called cooperative multitasking. Cooperative multitasking has an important shortcoming: latency. This is especially important for highly interactive applications. Let's say in this diagram, process 1 is a word processor application, process 2 is a web browser application, and process 3 is a video encoder program running in the background. The operating system starts process 1, which executes for 2 milliseconds and then has to wait for the user to press a key. So it returns control to the operating system, which decides to start executing the next process, process 2. Now let's say process 2 does some processing for 50 milliseconds and then has to wait for an I/O operation. It returns control to the operating system, which then decides to execute process 3. What happens if process 3 is very processor bound, has minimal I/O operations, and is not well programmed to consider other processes? In this case, the I/O operations of other processes might complete. For example, the user might press a key in the word processor application and expect the application to react and display the character on the screen. However, because process 3 is still executing, the user will experience noticeable latency. Cooperative multitasking relies on processes voluntarily yielding control, which can lead to issues if a process is poorly designed or is unresponsive. Another approach to sharing CPU time between processes is called preemptive multitasking. In contrast to cooperative multitasking, preemptive multitasking allows the operating system to take control, stop a process, and switch to another when necessary. There are many ways to implement preemptive multitasking, one of which is the round-robin approach. In this approach, the operating system gives each process an equal small execution time slice, which improves latency. But there is an issue with this approach as well. Processes have different characteristics, and this approach doesn't take these differences into account. For example, in this diagram, process 1, the word processor, is an I/O-bound application and spends most of its time waiting for input from the user. When it receives input, it processes it and displays the output on the screen. For the word processor, latency is important. On the other hand, process 3 is a video encoder running in the background and is processor bound, but latency is not as important for it. For example, the user probably won't notice a difference if the video encoding operation starts half a second late. In this case, what could happen is that process 1 spends most of its time waiting for input. When its turn ends, the OS switches execution to process 2. At this moment, if the user enters a key in the word processor, it has to wait for all other processes to complete their turns before it gets its turn on the CPU and process the user input. On the other hand, if we set a very short time slice to reduce latency for I/O-bound applications, processor-bound applications like the video encoder will have shorter execution times and frequent context switches, causing performance overhead. While round-robin scheduling is simple and ensures fairness, It may not be optimal for systems with a mix of I/O-bound and processor-bound processes. Modern schedulers are sophisticated and use various algorithms and policies to schedule different types of processes. To address the issue we saw with round-robin scheduling, the scheduler must take into account the different characteristics of processes. For example, some processes may be I/O-bound, which means they spend most of their time performing I/O operations such as database operations or API calls. For this category of processes, latency and responsiveness are important. On the other hand, some processes may be processor-bound, which means they spend most of their time using the CPU for tasks like mathematical calculations. For this category of processes, minimizing context switches is important. Now, let's explore a technique that some schedulers use to balance these two categories of processes. First, a scheduler defines a target latency. This value should be small enough to ensure program responsiveness, but not so small that it increases the overhead of context switches. For this example, let's assume the scheduler sets a target latency of 30 milliseconds. By dividing this value by the number of available processes, the scheduler allocates a proportional share of CPU time to each process. Additionally, processes may be assigned different priorities by the operating system or the user, which can increase or decrease their share of CPU time. However, in this example, we assume that all processes have the same priority. Now, let's assume that process 1 is processor-bound, process 2 is I/O-bound, and process 3 is also processor-bound. Initially, all processes have used 0 millisecond of their allocated CPU time, so the scheduler selects process 1. Let's say process 1 uses CPU for 8 milliseconds and then initiates an I/O operation yielding control to the operating system. The scheduler then selects process 2. Since process 2 is I/O bound, it uses the CPU for only 1 millisecond and then waits for I/O. In this case, the scheduler starts executing process 3, which is processor bound. Suppose process 3 has used 7 milliseconds of its allocated CPU time when the I/O operation that process 2 was waiting for completes. Since process 2 has only used 1 millisecond of its allocated CPU time, the scheduler will choose process 2 to execute next. This allows process 2 to immediately respond to the completed I/O operation without waiting for process 3 and process 1 to finish their turns, as would happen in a round-robin approach. Using this technique, which is similar to how the Linux CFS scheduler works, I/O-bound processes experience reduced latency and high responsiveness. On the other hand, processor-bound processes can use more CPU time without being forced to yield control, while other processes are blocked, for example, waiting for I/O operations. As mentioned earlier, modern operating systems are highly sophisticated when it comes to scheduling. In modern systems, the scheduler could even be modular, enabling different algorithms to schedule different types of processes. After reviewing how the scheduler shares CPU time between processes, let's explore the steps the operating system takes to switch from executing one process to another. First, it saves the state of the current process, including the program counter, a stack pointer, general purpose registers, and other architecture-specific data. Then the operating system updates its internal data structures for the process, such as changing its state from running to blocked. After that, the scheduler evaluates all the criteria and chooses the next process to execute. Next, the operating system restores the state of the next process, including the program counter, a stack pointer, general purpose registers, and other architecture-specific data. And finally, it resumes the execution of the next process. As you can see, a context switch involves saving and restoring data as well as computations to choose the next process. This introduces performance overhead, which is why the operating system and programs should try to avoid unnecessary context switches. Thanks for watching part 2 of this tutorial series. In this part, we explored how the operating system scheduler shares CPU time between processes, the steps involved in a context switch, and why minimizing context switches is crucial for performance. In the next part, we will dive deeper into the challenges of concurrent programming that software developers should be aware of. If you found this video helpful, don't forget to give it a thumbs up and subscribe to the channel for more tutorials like this. It's going to be an exciting journey, so make sure to stay tuned.